Okay, thanks everyone for coming, and thanks to those of you who are listening to us online. Yep, the title of the talk today is Scalable Streamlining the Ambient Noise Tomography. It's a method that has been around for about 20 years now, and it's been mainly in academia. So the aim of this talk and the aim of my work is to show the attempt that we have done to automate this procedure and to make it scalable and streamlined for industry and for other partners. First, I would like to acknowledge the country. I'd like to acknowledge the people of the country on which we meet. For those of us in the main office, I acknowledge the Ngambri and Ngunnawal peoples as the traditional custodians of the land on which we meet. Those cultures are among the oldest living cultures in human history. I acknowledge their continuing connection to lands, waters, and community. I pay my respect to the peoples, the cultures, and the elders, past, present, and emerging. This always was and always will be Aboriginal land. I also extend this same acknowledgement to the peoples of whichever land you are gathered on today. So yeah, my first slide is full of text, but I promise you this will be maybe this one and the next one will be the only ones with text from. But it basically outlines the workflow that is available for ambient noise tomography, and most people use this workflow. Usually a window of data is cutted. The original paper by Benson et al. 2007, which is over 1,000 citations, suggests to cut a daily window of data, normalize it in time, because you don't want directional energy from earthquakes. The work is supposed to capture and information or extract information from ambient noise. So you don't want earthquake signals, and that's done by normalizing the data in time. Then you normalize, sorry, I should point here. So and then you normalize in frequency, because your instruments are not recording all frequencies at the same level. And then you cross-correlate the data between two stations, and you stack or add all those cross-correlations up to obtain something called noise correlation function. I'll try to illustrate how this is done, but this is the outline of what has been practiced by many papers over 1,000 citations. But early on, but I think it was around 2009 that it was pointed out that if shorter windows of data are used, you get a better signal to noise ratio. You amplify the signal more. And that's purely based on the fact that, well, the ambient noise is surrounding us. It's everywhere. It's the main source of ambient noise is the interaction of ocean waves with the solid earth. It could also be anthropogenic noise caused by many other factors. But what's important is that they are surrounding us. And if we want to extract surface wave information, we cannot rely on one piece of information from one window of data. You have to do over and over, and you have to stack and the idea for stacking there is to cancel out the information that comes in perpendicular to the stations and amplify the information that is coming in from basically from 0 to 180 degree. So basically the area in blue and the two lobes area in blue, they contribute constructively to the construction of surface wave signals, but the ones perpendicular to our stations, which is at minus 90 and 90, they are destructive. So the idea of stacking is so that the ones that are at minus 90 and 90, they cancel each other out. And the ones that are at 0 and 180, they amplify each other. So that's the whole idea. In practice, we don't have a 180-degree distribution of noise sources of noise around our stations. Usually it's something like this. This is a study done by Prieto et al. 2009, where they looked at distribution of noise around California. And they realized that actually noise is not purely 180%, 180 degree, 360 around the station. It's usually coming in from a specific direction. But anyway, so how does it look? When you cross-correlate hourly data, you will end up something like this. So on the x-axis, I'm showing you time, okay? On the y-axis, I'm showing you the number of hourly cross-correlations It's like a matrix presentation of hourly cross correlations, and it goes all the way up to 60,000 of them. So 60,000 hourly cross correlations between two stations will give you data like this. And if you look at this, there's nothing in it. There's not much signal in that. I would like to mention here that codes that we have been using is developed by our geoscientific computing team here at GA. Our code is called HyperSeis, High Performance Seismological Tools. You can check it out. It's on GitHub. It's available publicly. And one person in particular, Rakib, who has been the main developer on HyperSeis. So, but what I would like to show you is that when you stack these information, when you stack these hourly cross correlations that contain all these background noise information in them, you will see how the signal rises. When you look at it for the first few hours, there's not much signal in it, but as soon as you pass 1,000 hours, you can see the surface wave signal emerging. And when you pass 10,000 hours, the signal is quite clear. And because in this case we have 60,000 cross correlation hours. These two stations are permanent stations. They've been recording for 10 years. So we have a lot of data, and for that reason, we get a very nice signal. So this is now a surface wave signal. You can see that long periods arrive early and short periods arrive later. I'll explain what that means in terms of Earth structure. But this is the basic of ambient noise tomography, basically. Now, one other step in this workflow is normalization in time. So you have to normalize your data in time. And one method that is widely used, both in passive and also active seismic, is called one-bit normalization. And that's when you take the amplitude of your signal. If it's positive, you make that 1. If it's negative, you assign -1. So 1 and -1, that becomes your data. I have done an example for that. Here's just background ambient noise. And I've set it to 1 and -1. So it captures most of what's going on in your data, but the good thing about it is that now the amplitude is only 1 and -1. And that's a huge compression. And compression is great because you can now compress this data into actually 2 digits, 1 and -1, instead of having the actual data recorded. But what I would like to show here is that there are problems associated with this. And originally, when this was proposed by Benson et al. In their original paper, was to suppress signal from earthquakes. Here you could see this is an earthquake recorded by a network, and the earthquake occurred in Papua New Guinea. Its magnitude is about 7.5, so it's huge, and it dominates the entire signal. But what one-bit normalization does is that it will bring everything to 1 and -1. So initially, at the beginning, it was thought that, oh, look, it's actually normalizing the data, again, back to 1 and -1. But I think there are issues with that, and I'm trying my best to explain it. So here I've done a cross-correlation for nearly 10 years of data on 2 quiet stations in the Outback, WRAB and WRKA. These are state-of-the-art deployment of our permanent network. And you can see when we filter the data below 0.1 hertz, there's nothing in it. Okay, there's no signal clear in the cross correlations. But when we look at it at about 0.1 hertz, there's a clear signal appearing every day in the signal. When you stack them all up, the signal is quite clear there. So in this case, when I use one-bit normalization, you do see that I lose the signal below 0.1 hertz. And that's actually quite important because below 0.1 hertz is the signal that we use to image mantle and crustal structure, which later on I will show you. But if I don't apply one-bit normalization, you can see that the signal is quite clear no matter which frequency band you look at. So this is again the same plot, but without one-bit normalization. And you can see that the signal is quite clear below 0.1 hertz and above 0.1 hertz. And when you stack it, you see the signal completely clearly rising. So it's quite clear that there is an issue with one-bit normalization. To further convince you, I plot an example. Here's a 1 day of data, one busy day of data on the left and one quiet data On the right, one busy data is the same magnitude 7.5 earthquake in Papua New Guinea, recorded by station WRKA in the center of Australia. And when we take the frequency time analysis of this signal, frequency time analysis is you divide your data into short pieces of short windows, and you take Fourier transform of them. And this is the amplitude of those Fourier transform shown in time. So you can clearly see the earthquake signal comes in and it dominates everything, but you can also see the aftershocks are also quite dominating and they're destructive in the background ambient noise. On the quiet day, however, there's no earthquake, so you can see the ambient background noise signal over there around 0.1 hertz. We have a peak at 0.1 hertz and we have another peak at 0.2 hertz. Now, when we do one-bit normalization, the idea is that you don't affect your data, which means that you don't touch the frequency content of your data. And you can see that to some extent for when you have only ambient noise, the background noise, there's not much difference between these two plots. But when we see earthquake, you can see a shift in where the maximum energy is coming in, okay? So these two are not actually the same anymore. This is more visible when we compare the phase. Here, what I'm plotting here is the magnitude of the Fourier transform. When I compare the phase of the Fourier transform, in this case, I'm subtracting the Fourier transform, phase of the Fourier transform from this image to this image. And I can clearly see that if you take on the right one, for example, the 0.1 hertz, the phase is untouched. So the phase of your signal remains the same. At 0.2 hertz, it starts to affect your signal, but then beyond that, it's chaos. It's basically has completely, one-bit normalization has completely altered the phase of the signal, damaging basically the phase of the signal. And that damaging is way more visible when we have an earthquake. So we should not be using, I think that's the conclusion here, that we should not be using one-bit normalization. And that is very clear in the previous example that I showed. If you use one-bit normalization, you lose the signal below 0.1 hertz. Okay, so if we don't use one-bit normalization, then how do we suppress the earthquake signal? Because they are quite strong and they are occurring and we are surrounded by them, for example, here in Australia. So what's the solution there? Well, here's my solution for this problem. This is station MEEC and EIDS over here. I've plotted all earthquakes that were recorded by these stations in this map. And I would like to draw your attention to the same argument that was made for ambient noise, that we should try to amplify the signal that is coming from here by stacking and suppressing the signal that is coming from perpendicular angles. So in this case, for example, all the earthquakes that are occurring in Japan, they're quite destructive, the ones that are coming from north, and the ones that are happening at the ocean boundary, plate ocean boundary, then they're also destructive. But the earthquakes that are occurring is over here and over here, they are constructive. So if we design a framework to incorporate where the signal is coming from, then we can use them. And this is my proposal to do this. In this work, we divide the Earth into cells of 1 or half a degree, and we calculate the azimuth from each cell in this worldview plot to the stations. And then we choose a threshold, for example, plus minus 30 degrees from these two stations, okay? And that gives you two lobes, basically one lobe on the right and one lobe on the left, very similar to what's expected from ambient noise tomography. And if you stack the signal in these two lobes, you get a good surface wave. But if you stack the ones that are contain information from earthquakes, you basically get rubbish. There's no information in there. That's the top one is the cross correlation and stack for the earthquakes that are perpendicular to the stations, and the bottom one, where you can clearly see the surface wave signal, is the cross correlation for earthquakes inside these two lobes. With this framework, you don't need to apply one-bit normalization, but at the same time, you suppress the earthquake, or I shouldn't say suppress, you use earthquake signal to help with the construction of surface waves. Okay, so that's out of the way. I think the last thing that I would like to mention, but that's for future work, I'm currently working on it, is whether we should actually stack everything. I don't think this is a good idea. Original idea was to stack. If you stack everything, the bad ones will cancel each other out. The good ones will play constructively, and that should work fine. But I'm showing you an example here for two stations. One is in Papua New Guinea, and the other one, I believe, is in Macquarie Island. The two stations here. And if you calculate the cross correlations and you stack them all up, there's absolutely nothing. There's no surface wave signal. This is the window of surface wave signal between these two black bars, and there's absolutely nothing in there. So usually in seismology, what people do is that, okay, that's just bad data, they throw it out. But what I would like to do is to figure out if there is actually this information, if the information about surface wave actually exists in these, I don't know, 100,000 cross correlations, and somehow we can actually extract them. But that's the topic. Maybe that's something for another presentation. Okay, so let's do some tomography, or just pick some dispersion curves. So here's an example of cross correlations that I've calculated. All the permanent stations that we have in Australia plus Osray 1. This was the first phase of Osray deployment during EFTF1. And you can see that clearly that the surface wave signals are showing up. Here I'm showing you X is a time axis, and vertical axis is the interstation distance. So closer stations are down here, and the further stations are up there. And you can clearly see that surface wave arrivals becomes later as the interstation distance increases. Okay, so but how do we use this data to image the Earth structure? That's the question that I'd like to answer next. So take the same station pair that I talked about, MEEC and EIDS. This is how their cross correlation looks like. I filtered them in 6 frequency bands. Down here at the bottom, this is the lowest frequency bands that I filtered in, 0.005 to 0.01 hertz. And you can clearly see that the arrival of this low frequency is earlier than the arrival of the higher frequencies. Okay, so the frequency, and this is what we call the dispersive properties of surface waves. Basically, if surface wave frequencies were all arriving at the same time, we wouldn't be able to image the Earth with surface wave. The reason that we can image the Earth is because different frequencies arrive at different times. And the reason for that is low frequencies, they're more sensitive to deeper structure. So they, for example, in this case, the 200-second signal is sensitive to convecting mantle. So it's very deep into the Earth. And Earth velocities increases with depth. So at depth, they travel faster. And at surface, they travel slower. That's why they arrive later. Okay, so now to derive this dispersion curve, or this is what we actually call dispersion curve. You don't see the curve yet here. Let me remove that. You don't see the curve here, but you can connect these dots yourself, and you will see that it is a curve. It's a curve that represents high velocity at low frequencies and slower velocities at higher frequencies. So how do we do this? Well, I'm using a method that was proposed in 1955 by Aki. And the idea is that if this is your signal as in time domain, you take the Fourier transform of that signal, you take the real part of that signal, which will look something like this in Fourier transform, and you compare that with you compare the zeros of this function, which every time you cross a zero, with the zeros of the Bessel function. Okay. Those of you who haven't heard of Bessel function, think of it as something like a sinusoidal function. It's just a function with this kind of shape, which kind of resembles what we see over here, not with amplitude, but in terms of where these zeros are happening. And Aki was the first person to discover this, and he realized that using a simple formula, the zeros of your 2 pi times the zeros of your signal, multiplied by the distance between the stations, in this case 256, divided by the zeros of the Bessel function, will give you a dispersion curve, which is what you will observe here. For example, here, I've calculated this, and the phase velocity on the y-axis, x is the frequency. So you can see at lower frequency, the velocity is higher, as it's suggested by the earlier arrival of this wave. There is an inherent ambiguity in this method, and that is you don't know which one of these zeros to match with which one of the zeros of the Bessel function. Basically, you can start from this zero and you get this dispersion curve. You can start from another zero and you get another dispersion curve. So usually what people do is that they calculate a range of dispersion curves, and an expert opinion, or we call it a seismologist, will pick the right dispersion curve. And what goes on in that picking process, and that's manual picking, is that we actually look at which one at the dispersion curve that resembles the Earth structure more. If you pick this one, you have to notice that your velocities, as you go up here, this one actually goes up and it flies off to infinity. So that means that the velocity at the deep mantle is infinity, which is not real. That's not a physically realistic value. But this, in particular, this dispersion curve, it's telling you that the velocity in mantle between these two stations is about 4.5. And that's exactly what we expect from a physical Earth. So, and this method has been used widely for the past 20 years to image the Earth structure. Here I'm showing you an example done by Ekstrom in 2009, where they imaged the continental US. This is I forgot what frequency band this was, but I think it's about 5 seconds. So basically at every frequency, we can create an image of the Earth like this, because these waves, when they travel through a layer in Earth, we can image that layer using an array of seismometers. This is what they have done in the US, where they used US array to image Earth at different frequencies. So now, the previous example, that's a textbook example. Okay, that's only 5 to 10% of every data set. Most of the data would actually look something like this, which is not realistic. This is telling us that the Earth is fast and it gets slow, and then it gets faster and then it gets slower. So it's wobbling. No, this is not a real Earth structure. We know that the velocities increase with depth. So we expect an image like this and not this one. So what's the approach to fix this problem? Well, in the previous example that I showed you, Goran and Ekstrom, they stop the search over here. So they say, no, this dispersion curve is not reliable anymore. So they move on to the next one. But what I've been trying to do is to develop an automated method that we can actually pick these dispersion curves without a human intervention, without someone actually sitting there and looking at these dispersion curves. Now, how do we know a dispersion curve or a data is good or bad in seismology? Golden rule in seismology, signal to noise ratio. So you pick a signal window, that's those yellow ones where I think my signal is. That's a surface wave window. I can estimate where I expect to see surface waves. And anything between them, that's noise, okay? So I can calculate the RMS of signal to RMS of the noise. I can calculate the maximum amplitude of signal to RMS of the noise, or I can calculate the maximum amplitude of the signal to the maximum amplitude of the noise. And then choose a threshold. Back in 2017, when I started this project, I asked Brian Kennett, what should I choose? What's the right value? And he said 2. And 2 sounds like a good number, you know. If the maximum amplitude in your signal is 2 times larger than your noise, then that's a significant signal. But then with that threshold, I actually threw out more than half of the data that we recorded from ASEG. For some reason, half of the data had signal to noise ratio less than 2. So, but we back then we had to publish, so we pushed that through. And that's the extended abstract, if you look it up, that we published during EFTF1. But now that I'm looking back at this, for example, these 2 cases, I brought them up. This one on the left, the signal to noise ratio is just slightly above 2. I think it's 2.001. And the one on the right is just below 2. It's 1.999. Now, but which one do you think is a good dispersion curve? Obviously, the one on the right, the one which will get discarded by this rule of 2, okay? Signal to noise ratio larger than 2. So signal to noise ratio obviously does not represent the dispersive properties of the surface wave. They just represent what it is, where there's something in the noise window and compared to what that thing might be in the signal window. It won't give you any information about how the dispersion curve looks like. So I developed a new approach for this. I realized that if you look at the data at close distances, the separation between the zeros is quite large. But as we go to higher frequencies, the zeros become closer and closer. As we go to larger distances, the separation between the zeros becomes smaller and smaller. So, for example, at 600 kilometers, you can see that the zeros are beginning very, very close to each other, whereas at 140 kilometers, they are spread out, okay? And by zeros, I mean, you have to imagine a zero crossing of these waves over here. So I plotted these on a map, on an XY graph, where I calculate the mean of these zero separation for each cross correlation, and I plotted it against an interstation distance. Okay, so that's the mean of zero separation. And there is a relationship. There is a clear relationship between these two graphs. It's a multiplicative inverse relationship, and it's precisely 1 over 0.63 times distance. Okay, so this is my rule now. If I have 2 stations, for example, this one, at distance 140 kilometer, over here, 140 kilometer distance, I go onto this graph. At 140 kilometer, I expect the separation between the zeros to be 0.01. And I draw that here, okay? That's a solid black line. And then I plot the zero separation between these in these waveforms on top of this. So you can see when the zeros are very close to this theoretical value that I can get from this graph, I have a very clear dispersion curve. But in the other example, so my dispersion curve will be this now. But in the other example, these bumps, these changes in the velocity that are unrealistic, they occur when we have a deviation we're missing a zero, or the zero is misplaced. In this case, it's actually caused by this tiny little problem over here. So this doesn't come up to, there's no zero, and therefore that zero is missed, and therefore your dispersion curve doesn't look reasonable. So I'm using this as a guide now. Whenever there is a missing zero, I go to the next branch of dispersion curve. Therefore, I obtain, instead of this green one, I obtain the red one, which is a more reasonable, realistic value. Another example, this is a more tricky one. So in this one, the zeros are not missed. They are just slightly misplaced, I would say. So for this, I actually calculate the gradient before and after, and I try to follow the gradient of the curve so that I obtain a smooth curve. Now, you might be asking, so how does this work when you compare it with the signal to noise ratio? Now we have a new way of computing how good a dispersion curve is, how good a surface wave signal is compared to the traditional method in seismology, which is signal to noise ratio. So I've plotted on the x-axis something what I call WZR instead of SNR. So WZR is the well-placed zeros ratio. So if the zeros are well-placed, that would be 1. So in this case, and do you see those points there? Everything is perfectly placed, and you will get a nice dispersion curve. And if it's lower, then you have problems in your dispersion curve. And the color here represents the SNR, the traditional SNR in seismology. So what I would like to draw your attention now, this answered my question that why Brian's rule of signal to noise ratio larger than 2 didn't actually work well in this case, in the case of ASEG. And that's because you can see that there are lots and lots of points which the zeros are well placed. This is a perfect dispersion curve, and it should be used. But their SNR is close to 0, so they will be thrown out. Okay, they will be thrown away. But that's not what we're doing now. So currently, I've changed all the procedures that we work with this, and we're using WZR instead of SNR. Now, I'd like to show you what does that do to the data. So if you don't use WZR, if you don't use my automatic approach to dispersion curve, this would be 15,000 dispersion curves that were recorded by the Oz array. Okay, and if you do tomography using these, that's what your Earth structure looks like at 5 seconds. I can see that Michael's eyes are already going like this isn't real Earth. This does not represent the Earth structure. Obviously, these bands of fast and slow, they don't represent anything realistic. But if you use our approach, this is how your dispersion curves looks like the toggle between those two, so that you can see how smooth they become, how more representative of the Earth structure. And if I redo the same tomography, now you can see this is the tomography that you would expect. You have the, I forgot the name, Amadeus Basin down here. You have some signature of the Nalia Basin over there. This is a newly discovered Carrara Basin up here. This is Mount Isa with high velocity. So now everything makes sense. Everything matches the geology. And that's because you have used the correct dispersion curves. So if I put this into perspective, I think it would have taken about a month of one person time, full time, to pick 15,000 dispersion curves. So this is almost instant. For 15,000, it takes about 5 minutes to actually run this. It's fully vectorized and significantly reduces the amount of time that we have to put into this. So let's look at some tomography now. So this is the same image. I'm just showing you the pixelated image of it. This is the actual image that we get from tomography. So the Carrara Basin is there quite clearly. Amadeus Basin. So these, I'm just using these to basically validate my work, because this is an automated approach. I didn't pick these dispersion curves, so I have to validate them against well-known or pre-existing models. In this case, I'm comparing it with Oz Seabase, which gives us a depth to basement in Australia. They know, and also the outlines of the sedimentary basins. So another feature in this model is the Nalia Basin. I was not expecting the Nalia Basin to show up in our ambient noise tomography model, just because it's quite small compared to other features here, but it's nicely showing up. This is a report from 1973, I think. Back then, GA was called BMR, and this is one of the first seismic lines that GA did over the Nalia Basin. So the method is working. Now it's fully automated, and we can generate these images. So what I would like to do next is to focus on this area, which we seem to have a lot of low velocities. This is our first phase of deployment, Oz Array 1. And what I would like to compare my work with are active seismic lines in this area. So this is a work from the basins team, a basin systems team here at GA. They identified this basin called Sub-Carrara Basin. This is the outline. I plotted the outline over here so you can see how nicely it matches the ambient noise tomography. But what more I can do is to look at the active seismic line in this region. The line is actually over here, so northwest to southeast. That's northwest to southeast, and this is the interpreted baseline that they have observed over here. Now, if I extract the seismic velocities from my ambient noise tomography and overlay it on a depth migrated image of this figure, it looks like this. So you can clearly see where this basin has been imaged. We see an extreme low velocity, which is showing up on this map too, but we see an extreme low velocity in this basin, which is quite nice to see actually. So moving on to, I have two other seismic lines that I'd like to compare with. This seismic line was deployed after they discovered the Carrara Basin. Then this seismic line actually starts in Carrara Basin and it goes further west and it crosses this low gravity anomaly. So the Carrara subbasin is located on a low gravity anomaly, and they were wondering whether this low gravity anomaly is also another basin or the continuation of the sub-Carrara of the Carrara subbasin. But in the seismic line, their interpretation, they see a basin here in the Carrara basin, which is this side, but over this low gravity anomaly, there's no basin. And I don't really remember how they interpreted this, but anyway, nothing. It's not a basin. So, and I was wondering, how does this look up in my ambient noise tomography? We clearly see that where we have the sub-Carrara basin, the low velocities are there. But when we enter this region, which is not a basin anymore, we can see that higher velocities come in. So the velocities here below 2.5, that's where I would say that's a basin. That's a very loose, low density and low velocity material. But anything with the color yellow, or anything with the yellow and orange and above, that's not a basin anymore. That's a much stronger structure. That's a basement, basically. And then another cross-section, another seismic line over here, which again, you can clearly see the Carrara subbasin, and then it completely disappears. So there's nothing here. And we do observe exactly the same in ambient noise tomography. So I guess the purpose of this practice was to see whether the result from ambient noise tomography is actually comparable with the active seismic. The passive seismic or the ambient noise tomography is extremely cheap compared to active seismic. Active seismic, each one of those lines is on the order of 10 million, on the order of millions of dollars. That's how much it costs to run those lines. Whereas the entire Oz array costs, I think, with today's cost would be like $3 million. So it's not comparable. It's this is a way cheaper, non-invasive method. It's not exact. It won't give you the same resolution. Obviously, the resolution that you would get with the active seismic is extremely, it's great. It's down to hundreds of meters, whereas here we are to 25-kilometer resolution. But to see that the results are comparable is actually quite nice. Now, what we could do more is to look at this model in depth in places that there aren't any active seismic lines. So there's no active seismic line over this low velocity anomaly in the top left corner. And you can clearly see that there is, so I'm plotting the Oz sea base, the depth to the basement from Oz sea base on top of this. That's this line over here. And I'm plotting the seismic velocities from A to B across this in this cross section. So there is a basin clearly here down to at least 3 to 4 kilometer, which is not imaged by Oz sea base, and we don't have any active seismic line to know about it. But clearly, ambient noise tomography is telling us. Moving to the right, again, that basin is that low velocity structure is still there. Moving further to the right, again, that low velocity structure is quite persistent, down to this time maybe 5 kilometers. So I guess that's, to me, this is a sort of a full validation that we can automate and streamline ambient noise tomography. This is still a work in progress. So the codes and the things that I have developed, the papers that will be written about, will be out there by the end of EFTF, which is June next year. But I'm showing you the results here. Okay, so the results that I've shown you is for this network. Yeah, if I can get the mouse there. For this network over here in Northern Territory, this is the distribution of our permanent network, and this is the current network that we have recording out there. It's been recording for about 6 months, and it will be recording for another 6 months or hopefully up to a year. So stay tuned for the results that will be coming out for this deployment. And lastly, I would like to talk about some of the challenges of ambient noise of deploying passive seismic networks. So a lot of the areas that we went to, especially in Northern Territory and Western Australia, there has never been any seismic instruments in there. They're actually as unexplored as the ocean bottoms, because we rarely have only ocean bottom seismometers around the world. And these areas are as unexplored as those. So going there, access is quite challenging. It's a harsh environment. And I think I would like to mention one of the contractors here, ASEG Geophysics, that we work with them. They've done a great job. They use helicopters to access these points and deploy these seismic stations. We have come up with our own setup of seismic station. You can see that it will look something like this out there in the field. There's a solar panel facing north, a battery and a recorder is under the solar panel, and the actual sensor is 0.5 meter into the earth. But this doesn't mean, compared to active seismic, you can see that how non-invasive this method is. You basically set up a tent, a small tent like that, and you leave it recording for 1 year and no one would notice. Well, that was our first thought. It's not always like that. Obviously, I think a cow must have sat on this. I don't know how this happened, but it's completely destroyed. And for some reason, the GPS antenna that we have here attracts wildlife. And this is a photo that I've taken 5 years ago. I was really surprised. This is a GPS cable that is completely chewed off. And yeah, so it has its own challenges. The stations must be serviced. But I think it provides great information, and I'm hoping that we can continue this work. So easy to deploy, non-invasive operation, cheap to operate and maintain, provides 3D volumetric images of the seismic wave, and I have developed a scalable and streamlined approach for ambient noise tomography. Thanks for listening.
Do we have any questions from the room? Yeah, then.
So an excellent talk. Thank you very much. I noticed that the new array, it's Australia-wide. It's much larger spacing than the arrays you've shown the examples from. What are you trying to image with the larger Australia-wide arrays? Is it really the deep earth structure, the lithosphere? Or?
So I'll repeat the question. That's an excellent question. Thank you very much. So the question is, what is the motivation, I guess, for this large array? Are we trying to image the deeper structure? The answer is yes. So now we are hoping that we can provide a lithospheric image, full lithospheric image for Australia, because the results that I shown this talk about Oz array phase 1, we do have an image down to 80 kilometers, but for the purpose of this talk, I only focused on the top 20 kilometers. That's where I validate my model to see whether it matches the surface geology and what we know. But that model is deep. It goes down to 80 kilometers. And with such a wide network, with such a concurrently recording set of stations, we can go down to 200 kilometers. Yes, that's the answer to your question.
Any more questions? Okay, that's one more question.
I'm assuming that you have to have the permanent stations spread around to complete the cross correlation.
So yes, they will help in the sense that there will be a cross correlation between every permanent station and every temporary network. So it will provide additional rays, additional coverage, and it will improve the resolution. But even without the permanent station, this network properly covers Australia. So just data from this network, I think it's enough to provide a lithospheric image for Australia. But yes, so that just because we do have the permanent network, we will definitely use the data.
But for your original smaller inverted commas arrays, you really needed those remote permanent stations.
No, because these networks, like this smaller network over here, they are recording at the same time. So we will calculate cross correlations between those stations that are recording at the same time. Actually, I have used one station, this Warramanga array station, in the middle of the net, just because it was in the middle of the network, and data had overlap with every other station in the network. So I have used it. And in the previous one of the images that I showed, this surface wave into larger distance, up to 4,000 kilometers, we do have those cross correlations. It's just that we haven't used them to image the structure yet.
We
well, at least with other the Southern Ocean itself is quite different from a shallow seas to the North. Do you see that when there's getting ready to great field, and do you think it has an effect on the results, so that it can process it?
So
But if the noise to it, in other words, it's anisotropic, then it's going to look at the
So that's a very good question. So the question is, the distribution of noise, of the sources of noise, is not anisotropic. So it's not distributed homogeneously around, right? What do we do with that? So actually, the examples, I didn't mention it, but sorry, it's not really sure where am I? Yeah, okay. The examples that I showed. Yeah, if I can go to smoke, yeah. So for example, take this one. That is a that signal, so that's a surface wave, that's the surface wave, on two causal and acausal windows. But this signal in between, that's the Gulf of Carpentaria basically ringing. Okay, so there is clearly an anisotropic distribution of sources of noise everywhere. But what this method is trying to achieve, what the automated part is trying to partially answer your concern, is that it doesn't matter where the source of noise is coming from. As long as you have a signal like this, you can cut a window of causal and acausal as your surface wave. You're taking a Fourier transform of that, and now you're in frequency domain. So you don't really care where is that data coming from? Where was the distribution of noise around that station? And you will compare with the zeros of Bessel function, and using this law, you will measure the quality of your dispersion using that. So I kind of disconnect the work from being dependent on where the source of noise is coming from. In that sense, I understand that there will be cases that this will not work. For example, if you are close to a volcano and there are small earthquakes that are continuously bombarding your seismic deployment, then unless you have a very detailed catalog of those earthquakes, which you can take out those windows of earthquakes and use ambient noise, I don't think there is any other way to really fully address that question.
Questions online? No more questions? Then we close the talk. Thank you again, Babak. Cheers.